Hey there, it's Toby. Welcome back. We're going to continue walking through the LLVM tutorial from llvm.org. We're in the latter part of chapter 4, and we were successful in creating the JIT, the just-in-time compiler. I'll show it to you briefly. So if I do an expression like 4 times 5, then it'll generate the LLVM IR code, compile that into machine code, and then execute the machine code and get the answer. Okay. And that is pretty cool stuff. So let's continue reading this chapter and see what else the author has in store for us. I actually don't know the name of the person who wrote this tutorial. If I find their name, or it could be multiple authors, I don't know, then I will definitely give them credit later. Okay, so this is basically working. The DOM of the function shows the no argument function that always returns double, that we synthesize for each top-level expression that is typed in. This demonstrates very basic functionality, but can we do more? So he's saying let's make a test function that does some calculations. All right, let's do what he does. All right, that compiles the function, and then we're going to call this test function, and it'll actually do it, pass in these values and executes the code within test function. If we try to run it again, it fails because every single time it destroys the global module after executing something, and that is hilarious. So I guess we're gonna fix that next. So function definitions and calls also work, but something went very wrong on the last line. That call looks valid, so what happened? As you might have guessed from the API, a module is a unit of allocation for the JIT, and test function was part of the same module that contained anonymous expression. When we removed that module from the JIT to free the memory for the anonymous expression, we deleted the definition of test func along with it. Then when we tried to call test func a second time, the JIT could no longer find it. The easiest way to fix this is to put the anonymous expression in a separate module from the rest of the function definitions. Okay. I see. The JIT will happily resolve function calls across module boundaries as long as each of the functions called has a prototype and is added to the JIT before it is called. Okay. By putting the anonymous expression in a different module, we can delete it without affecting the rest of the functions. In fact, we're going to go a step further and put every function in its own module. Doing so allows us to exploit a useful property of the Kaleidoscope JIT that will make our environment more repo-like. Functions can be added to the JIT more than once, unlike a module where every function must have a unique definition. When you look up a symbol in Kaleidoscope JIT, it will always return the most recent definition. Interesting. Okay, it's showing us that if you define foo, call foo, redefine foo, you call foo, it'll always execute the most recent definition of foo. So to allow each function to live in its own module, we'll need a way to regenerate previous function declarations into each new module that we open. Interesting. Okay, I guess we need this get function. Do we already have a get function? I don't think so. Let me close this VLC program that I have running here. Okay, let me see. Do I have a get function? I'm calling a get function method, but I don't have a get function. Okay. So we're gonna add a get function apparently, which it first asks the module to get a function to see if it's already been defined. The function with that name has already been defined. If not, see whether we can code gen the declaration from some existing prototype. Oh, we're gonna have a map that caches our function prototypes. I see. And then if we find it, we're gonna code gen it again and return that. I see. Okay, I understand this. I'm just gonna copy it. Put this near the bottom. Okay, so we're gonna make a map, make this function protos map, I believe, which is a map of AST pointer to AST node, I think. And then later on in the code gen of the call expr AST, we're gonna change it to call get function instead of the module get function. That makes sense. Let's go to call expr AST code gen, and we're changing this to call the get function. I think we need a forward declaration for it to be able to use it. So I'll put the forward declaration here. And then in the code gen method of function AST, we need to transfer ownership of the prototype to the function protos map, but keep a reference to it for use below. Very interesting. Okay. Okay, let's go there. So this function AST colon code gen. I'm going to, let's see. First of all, change this to get function. But before that, we're gonna, what is this? Get a so P, I guess P is the actual proto. Yeah, okay. Do we need to do that? I'll do it like that, but part of me is questioning whether that's actually necessary. Or I mean, I already got the name here. It's only using P to get the name, so I'm not gonna do this. I'm not gonna do this auto P thing. Okay. I think it's fine. Okay, let me copy this code line by line because I wanna absorb it better. Alright, so I'm going to, I still haven't defined the function protos map. I already have the name in this variable, so I'm just gonna use that. Standard move proto. And then, yeah, I guess then if we didn't have the function, if we don't have the function, we actually not gonna do proto gen here. No. If we don't have the function, we just return the null pointer, which we already had this part here. Got it. Okay. I think this is good. We do need to define function protos, which would be a standard map that contains whatever that is, which is it's a unique pointer to a prototype AST. So let's define that. So it's a map that takes a string, or the keys are strings and the values are unique pointers to prototype AST nodes. Function protos, plural, yeah, okay. Okay, now to enable this, we'll start by adding a new global function protos that holds the most recent prototype for each function. We'll also add a convenience method get function, right. Our convenience method searches the module for an existing function declaration, falling back to generating a new declaration from the function protos if it doesn't find one. In call expert AST codegen, we just, which is here, we just need to replace the call to the module get function. Yes, I went through this. We also need to update the handle definition and handle extern, like so. So, we update it by, we want to add the module to the JIT, and then reinitialize the module and passenger here. Okay. And then for handle extern, we want to, I guess, take this proto, because an extern is a prototype of a function, and we're gonna stick it into the function protos. Okay. Sounds good. In handle, okay, yeah, we're gonna recompile it, and according to the author, it works. Let's build it and see if it actually works. If we can build it. Undeclared prototype AST. We need a for declaration, I think. Okay, I guess I will do a forward declaration. I don't know. I don't really know how to organize C++ code. I think that compiled, so let's run it. So, all right, what is the test that they, oh, okay. So if you redefine a function, it should work. First of all, if you define a function, it shouldn't go away after the first time you call it. So foo of 2 is 3. What about foo of 5? 6. Great. Now we're gonna redefine this function. Foo of 5 is now 7. Okay, it works. Beautiful. So even with this simple code, we get some surprisingly powerful capabilities. Check this out. You can define extern sine and cosine. Now you call it. Oh, you already get sine and cosine because sine and cosine are defined in the standard C library. I think that's what they mean. Sine of 4. Yeah, who is it? So yeah, external functions just work, and we're taking external functions from the C library here. So whoa, how does JIT know about sine and cosine? The answer is surprisingly simple. The Kaleidoscope JIT has a straightforward symbol resolution rule that it uses to find symbols that aren't available in any given module. First, it searches all the modules that have already been added to the JIT, from the most recent to the oldest, to find the newest definition. If no definition is found inside the JIT, it falls back to calling LLVM sine on the Kaleidoscope process itself. Since sine is defined within the JIT's address space, now it fallbacks to calling dynamic symbol sin on the Kaleidoscope process itself. Since sine is defined within the JIT's address space, it simply patches up calls on the module to call the LLVM version of sine directly. But in some cases, this even goes further. As sine and cosine are names of standard math functions, the constant folder will directly evaluate the function calls to the correct result when called with constants like in the sine 1 above. In the future, we'll see how tweaking this symbol resolution rule can be used to enable all sorts of useful features, from security, restricting the set of symbols available to JIT code, to dynamic code generation based on symbol names, and even lazy compilation. One immediate benefit of the symbol resolution rule is that we can now extend the language by writing arbitrary C++ code to implement operations. For example, if we add this function, put shard function, note that for Windows we need to actually export the functions because the dynamic symbol loader will use get proc address to find the symbols. That thing for Windows. Okay, so now after this we can produce simple output to the console by using things like extern put shard 120, which prints a lowercase x on the console. Wow. Similar code could be used to implement file I/O, console input, and many other capabilities in Kaleidoscope. This completes the JIT and optimizer chapter of the Kaleidoscope tutorial. At this point, we can compile a non-Turing complete programming language. Okay, I guess we're gonna go do something Turing complete next. Next up, we'll look into extending the language with control flow, structs, constructs, tackling some interesting LLVM IR issues along the way. So let's try to put shard, but I think it means put char, which takes a double. We'll put that into the code. Recompile. Okay, it compiled, and so let me try extern put chard x, And let me try put chart 48. Yeah, there's the 0 that got printed. Nice, because 48 is the ASCII code for 0. Put chart, I don't know, 67. That's C. Awesome. Yeah, we can externalize these functions written in C to this programming language that we've created. That is really cool, and the JIT is really cool. Basically, to put it in perspective, basically we've managed to complete the whole pipeline in compiler design. In particular, we've taken some code that is written here, let's say 1 plus 1, put it through the parser, which we wrote in chapters 1 and 2. The parser generated some AST code, AST structure. We translated this AST into, I guess, this code gen. We have a bunch of code gen methods, which, when combined, converts this AST to code in the LLVM IR format. And then we've taken this code. Whenever we take this code and say add it to the module, I believe. Let me when we add module, I believe that's when the code gen actually happens. So it's this point, I believe, when the JIT, we call it the JIT add module, because we've added the functions to the module, and the module is just a representation in IR. But when we add the module, which is an IR representation, to the JIT, that's when the JIT will actually compile the code into machine code. So we take this guy, go through the JIT, and the JIT generates machine code. Which we're gonna execute. We execute this function, this machine code. It generates this machine code. We send it to the CPU, and the CPU gives us back the result. We have completed this entire pipeline, which is usually a number in this programming language. And the place where that happens is when we do this weird get address. Get address gets us the address to this machine code, and then it exposes it to us as a C function, which we can call. And when we call it, it sends this machine code to the CPU. The CPU executes it and gives us the result. So this is the final picture that we have, and I'm very proud of myself for getting this far, and I'm proud of you for staying with me thus far. Yeah, I'm gonna stop this episode here, and in the next episode I'm gonna get into chapter 5.